All right, let's get started here. We're getting into section 5 and 6. So we're going to be talking about vapor pressure and looking at phase diagrams. Well, initially when we talk about phase or vapor pressure, we're talking about this idea of molecules moving from liquid phase and going into the gas phase. Now, as at any temperature, some molecules of a liquid are going to go and escape into the gas phase. It doesn't matter if it's really low temperatures. Some are just kinetic energy wise, a few are going to have enough energy to go into the gas phase. It's just what's going to happen. Now, as the temperature rises, that fraction or that number of molecules that has enough energy to escape will increase. So if you look at that diagram below, you've got lower temperatures, you've got a smaller fraction of the total molecules that have enough energy to escape into the gas phase. And obviously as temperatures increase, that kinetic energy bump or shape spreads out, and so you end up having more molecules or whatever the substance is having enough energy to escape into the gas phase. So vapor pressure, as more molecules escape the liquid, the pressure exerts, there's more pressure exerted on whatever, if it's in a container, it's going to exert some pressure as more of that liquid goes into the gas phase. And obviously, in this example here, you could measure that pressure by connecting it to some manometer where you have a level of mercury, and then you can measure kind of how that mercury rises depending on the vapor pressure formed. So the liquid and vapor eventually reach a state of what's called dynamic equilibrium. And the reason, so equilibrium is when two things are basically are equally balanced. Okay, so in equilibrium. You might think of being on one of those kind of balance boards. It's got the little round thing in the middle, and you're balancing your feet on either end. You're kind of trying to create equilibrium. You're kind of rocking back and forth. Same thing or a similar thing occurs between liquid and vapor state. So although you have molecules that are in the vapor state, you have molecules that are in the liquid state, you're constantly having molecules leaving the vapor state going back into the liquid state, and then also having molecules in the liquid state going up into the vapor states, but it's at equilibrium. So as many that are returning to the liquid state, that many are going into the vapor state. So it's kind of this back and forth, what we call an equilibrium. When we look to determine the vapor pressure of something, you can often determine, so vapor pressure is really just like, what does it take for this thing to go into the gas phase? So the boiling point of a liquid is the temperature at which its vapor pressure equals atmospheric pressure. So there's always going to be things that go into the vapor phase, even if it's very cold. But the boiling point of a liquid is kind of the temperature that is needed for anything to go into the gas phase. And depending on the temperature and the pressure, more or less will go into the gas phase. So the normal boiling point that's typically given, like in literature, is always in reference to 760 torr, or 1 atmosphere. So our examples here, we have diethyl ether with a boiling point of 34.6, ethyl alcohol of 78.3 degrees Celsius, as well as water being 100 degrees Celsius. And then we have ethylene glycol, and obviously this table does not show the increased temperature or the level of temperature needed to get to the boiling point for that substance. When we talk about vapor pressure, liquids transitioning from melting to freezing, you can have what's called a phase diagram. And a phase diagram basically communicates in what areas in relation to pressure and temperature, in what ranges things would be solid, or things will be liquid, or things will be a gas. Okay, and the areas between, so the lines indicate the equilibrium that's present between phases at those points. So you have the area where melting and freezing occur. You have the area where vaporization and condensation occur, and you also have the area where sublimation occurs. So let's look at these these regions individually. So the circled area here indicates the liquid and vapor interface, what we would refer to as like boiling, right? The boiling point, that area. So the area is measured between the triple point, okay? So it starts at the triple point, or that T, and the triple point is a really unique um, temperature pressure relationship where basically the substance is at equilibrium both with the solid, the liquid, and the vapor all at the same time. So they're all at equilibrium in the same location. It's a rather unique uh, point. So, and it extends all the way up to the C there, or what we call the critical point. And the critical point, beyond the critical point, there is no difference between the behavior of the liquid of that substance and the gas of the substance. They both they behave the same, and so we call that a supercritical fluid, because it's not a liquid, it's not a gas, it's they're indistinguishable. You can't tell the difference between the two. So any point along this particular line is what will be the boiling point for that substance at that particular pressure. Now this second line here, now this line represents the interface between the liquid and the solid. So this is when things melt. This is the temperature at which things melt depending on the pressure. Now below the triple point, the substance can't exist in the liquid state. It doesn't exist. And so along the circled line, the solid and gas phases are in equilibrium. The sublimation point at each pressure is along this line. So when we think of carbon dioxide, now obviously carbon dioxide sublimates between a solid straight to a gas. So at room temperature, and and specifically, temperature isn't the issue, but at normal atmospheric pressure, it's not enough pressure for carbon dioxide to be present as a liquid. So you would need a much higher pressure to get beyond the triple point, so that you could see the solid of carbon dioxide go to the liquid first before it goes into the gas phase. Now, if you notice some of the other phase diagrams, water has a really interesting, it's a slightly different phase diagram. So we have a high critical point. So note the high critical temperature and the critical pressure for water. It's really high pressure, really high temperature. And so these are due to the strong intermolecular forces that water has. With that hydrogen bonding really impacts the phase diagram that it shows. The boiling point, the freezing point, its critical point, its triple point, all those things are related to those van der Waals forces and how attractive those water molecules are to one another. One thing also that you might notice with water is that the slope of the solid to liquid phase line is a negative slope. All the other slopes that are in your textbook that you're most likely come across have a positive slope to that line, meaning that as the pressure increases, typically the solid tends to go to stick around longer. But as the pressure increases for water, the water tends to stay or move into the liquid phase rather than move towards the solid phase. So this means that as the pressure is increased at the temperature just below the melting point, water goes from a solid to a liquid. So it moves into the liquid phase, which is different than most other substances. So here is an example of carbon dioxide, which I kind of talked about a little bit. So carbon dioxide cannot exist in the liquid state at pressures below 5.11 atmospheres. So carbon dioxide does not exist. You cannot have liquid carbon dioxide unless you have a pressure of 5.11 atmospheres or higher. It just cannot be done. And so obviously when you have like carbon dioxide, on the table or in some punch bowl for a Halloween celebration, you're not going to have the liquid phase. It's going to go straight from the solid to the gas phase. One of the benefits or interesting things about, so if you look at kind of the critical point of carbon dioxide, so you need a pressure of 73 atmospheres and a temperature of 31.1 degrees Celsius. So that temperature, pretty easy to reach, and that pressure, 73 atmospheres, although that might sound like a lot, and it is significant, it isn't insurmountable when it comes to, when it comes to finding or getting just the right type of situation with carbon dioxide. So the low critical temperature and critical pressure for carbon dioxide makes supercritical CO2 a good solvent for extracting nonpolar substances. So liquid carbon dioxide or supercritical carbon dioxide can be used, superfluids can be used to extract nonpolar substances. And if you think of it, carbon dioxide is also a very cheap substance. So if you're trying to do this process, it can be a really affordable way to extract nonpolar substances that normally would take more either like expensive solvents or just more hazardous substances to solve it. All right, and that's it, and we will head into solids on Monday. So have a good day, and we'll talk to you on Monday.